Okay, welcome. Today we're going to complete our study of the Klein-Gordon field, the quantum Klein-Gordon field, by working out how the Lorentz group is unitarily represented on the space of states of the Klein-Gordon field. So as you recall, in our previous discussions of what is a relativistic quantum field theory, we came upon the requirement that the Poincaré group must be unitarily represented on the space of states of whatever field, whatever quantum theory we want to call a relativistic quantum field theory. And because we're allowed to ignore a phase in quantum mechanics, states are only defined up to a phase, then we could allow ourselves a little more freedom and talk about projective unitary representations. So that's what a relativistic quantum field theory is. And I gave you various heuristic arguments for why we needed a theory of fields rather than a single particle theory to give us a healthy, well-behaved relativistic quantum field theory. I gave those arguments in the first lecture. And what we've done so far is we've constructed a space of states, a Hilbert space, and a generator of time translations, H, for a theory, a candidate theory for a relativistic quantum field theory. And this generator of time translations is this Klein-Gordon operator, which is written so. And the Hilbert space H, we explored that in the previous lectures. That's the space of states you get by applying creation operators to the vacuum state. So it's the span of all states of this form under countable linear combinations, finite linear combinations, and then the closure of this space with respect to some norm. Okay, so we've got a candidate Hilbert space, we have a candidate time translation generator. We've explored some of the symmetries of the Poincaré group in the previous lecture, and we've also convinced ourselves that this theory is causal, so it's all signs point to this being a relativistic quantum theory. Today we want to conclude this discussion and actually supply a representation for all the generators of the Poincaré group on this Hilbert space. This is not something you usually find in the textbooks, but I think in terms of thinking about a relativistic quantum field theory as supplying a representation of the Poincaré group, it's necessary. I don't think that a discussion purely in terms of the causality of the propagators really gives you that, it really satisfies that requirement. So, but to do this today, I'm going to have to take a little digression on continuous groups of symmetries. So it turns out the Poincaré group is not a discrete group, it's an infinite group in the sense that it has an infinite number of elements. It's also a continuous group, meaning that it depends continuously on some number of parameters. It's a manifold. And there's a very beautiful theory of continuous groups of symmetries, which I sadly won't have time in this course to do justice to. So all the beautiful rigorous maths I will have to throw out the window, and I'll just leave you with a kind of physicist highlights of this theory. That's the objective today, to give you just the bare minimum of the theory of Lie groups and Lie algebras that we require to convince ourselves that the things we write down have got something to do with the representations of the Poincaré group. The full theory is very beautiful, very classical, very well established, and you'll no doubt encounter it in the future in some course on symmetries or groups that you may or may not take, or in just looking in textbooks. Now the main idea when you study a group that has a manifold structure, so it's like some continuous dependence on parameters, is that you study symmetries in the group that are very close to the identity, and then you use your knowledge about these elements close to the identity to tell you about large elements by exponentiating. That's the full story already. So I'm going to draw a picture. So we suppose that the group is also simultaneously a manifold and that the group operations are continuous. Now there's a distinguished point in this manifold, that's the identity, because every group has an identity element, so we can, there's a distinguished point in this manifold right there, corresponding to the identity. So every point in this manifold is an element of the group. And the operations of G, well, of M cross M goes to M via multiplication. Is continuous, and so is the operation of taking an inverse. So we have a continuous group when the operations, when the group, the elements of the group are points in a manifold, and the operations of multiplication and inverse are continuous in the natural topology that you would put on these manifolds. And I've tried to draw the manifold here of a group as a kind of curved surface here. That's not a bad cartoon. That's actually a pretty good caricature of what a Lie group looks like, as we'll see in some examples soon. And there is one element that's very special in this group, and that's the identity here. And so the whole idea of the theory of Lie groups, so Lie groups are examples of groups where the operations of multiplication and inverse are continuous. The whole idea of the representation theory of Lie groups is to study elements that are very close to the identity. So that we're going to, you imagine drawing a plane tangent to the surface, yeah? So this is meant to be the tangent plane to the identity. And then you study elements in the group in a small neighborhood around the identity. And Taylor's theorem ensures that the closer you get to the identity, the better this tangent plane is as an approximation to this manifold at all. So I'll write this down a little bit more precisely. And why we are talking about this at all is that the Poincare group is an example of one of these continuous Lie groups. We're going to study elements G of this group that are infinitesimally close to the identity. So to say this approximate, this needs a metric. But there's usually a very natural metric. Because we're going to study only very simple examples, we don't have to worry too much about this metric. There's always be one that's obvious from the context. So to understand continuous Lie groups, so groups that have the operations of multiplication and inverse being continuous, we study elements that are infinitesimally close to the identity. So the inverse operation is a continuous map from M to M. And to do that, we're going to approximate this region by this tangent plane. Or tangent space. Denoted T with an I, M. So this is the space of tangent vectors to the identity of the manifold M or the group M. That's what we're going to study. We're going to study that space as a model for the whole group itself. And then it turns out that we don't lose much in doing that for certain special Lie groups. This is a linear space, and it's called the Lie algebra. And we'll get to the algebra bit later on today. Because it's a linear space, it's a vector space, we can find a basis. It's always going to be finite dimensional in the examples we consider in this course. And we just write some basis of vectors for this space as xj. And now I'm going to do some examples so you have something in mind. We'll focus on compact well, no, they're not all going to be compact. We'll focus on 2 compact Lie groups and 1 non-compact one. I'm going to focus on 3 examples. So the first one is the group U1, the group of 1 by 1 unitary complex matrices. So the group of 1 by 1 complex matrices is pretty simple. It's just the complex numbers. And the unitarity condition shows you that it's not just any complex number, it's a complex number with norm equal to 1. So it's a set of phi in the complex numbers such that the norm of phi squared equals 1. So that's our very first continuous group, our first continuous Lie group. And you can check that the operations of taking an inverse and multiplication are indeed continuous. In the standard topologies, it's not so difficult. And let's study the tangent space to the identity. So what's the identity for the Lie group U1? Well, the identity is just the number 1, right? The number 1 under multiplication is the identity for this group. And so an infinitesimal translation, element near the identity has to be something that's near the identity. Has to be. So it's the set of all numbers z such that 1 plus z, we've got to take this condition and enforce it locally near the identity. So we got that 1 plus z, complex conjugate 1 plus z, it's got to equal 1. So the tangent space is the space of all numbers z such that this equals 1 to order z. And then, if you work this out, or actually, yeah, I'll put the epsilon in to order epsilon. So z are numbers, epsilon is an infinitesimal, so this makes it a nice linear space. And the condition, this condition here, you can quickly expand out the brackets, check it to order epsilon, and you end up with the condition that real z has got to equal 0. So to be an element of the tangent space to the Lie group U1, to be an element of the Lie algebra, is equivalent to being a pure imaginary number. And that's indeed a linear space, right? A one-dimensional linear space. So that's our first example of a Lie algebra. It's a pretty boring one, but it is our first example. Let's do a slightly more complicated one. Actually, more or less the most complicated one we've had so far. And sort of amazingly, this next example is sufficiently rich that once you understand it, the theory of all other compact semi-simple Lie groups is reduced to kind of various copies of this example. So it should be every physicist's favorite example, right? It's the rotations. Let me see, did I do SO3 or O3? I did SO3. So rotations in Euclidean space, not including inversions. SO3 is the set of 3 by 3 matrices O such that O transpose O equals the identity. Yep.
Why is this a Lie algebra? Because I think we need a Lie bracket, don't we?
We need a Lie bracket, don't we? Yes. Why is this a Lie algebra? We're going to talk about the Lie bracket later. Okay. So far, it's not a Lie algebra. All I've just written down is a linear space. To be an algebra, you need not only a vector space structure, but a product structure, an associative product. We're going to write one down later. It's a pretty boring one for this Lie algebra, though. So the exactly. So there's not much to it. It's an abelian Lie algebra, so there's not much that's going to happen on this particular example. But this example, this is going to be a bit different, as we'll see. Okay, I'll remove the S so that we can just keep it simple. It'll be disconnected, but that doesn't matter. So the tangent space to the identity of the group of rotations is the set of operators, matrices X, such that the identity plus an infinitesimal amount of X transpose the identity minus an infinitesimal part of X is the identity to order epsilon. So that's that condition above. And you can just work it out, and you find that that's the same as the set of matrices X. Sorry, there's a plus there. This is equal to the linear space of 3 by 3 matrices such that X plus X transpose equals 0, otherwise known as antisymmetric matrices. And then we could ask questions of this linear space. This is our first non-trivial Lie algebra. We haven't given it an algebra structure yet, but this is our first non-trivial example. The dimension is 3. You can work that out. And we'll give a basis. So to give a basis, you just need to find 3 antisymmetric 3 by 3 matrices that are orthogonal with respect to an inner product that I haven't told you about yet. So any antisymmetric 3 by 3 matrix is a linear combination of 3 basis matrices. What did I call them here? J, of course. And I'll write them out. And this is not the only choice that works. You know, bases aren't unique. To be a basis, there's not a unique basis for a vector space. It's an arbitrary choice. So I just made this choice here. And that's one possible basis of elements of this linear space. You take these 3 by 3 antisymmetric matrices. And our last example, this is the big one. This is the one that is interesting for us in relativistic quantum field theory. It's the Lorentz transformations. So the Lorentz transformations are a subgroup of the Poincare transformations, and that's the hard subgroup, so to speak. We've done the easy subgroup, the translations. Now we're going to do the hard one today. It's the Lorentz transformations. We've actually already met this group. It's the set of 4x4 matrices lambda such that eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma. And indeed, we've already met the tangent space to the identity of this group. So that's the set of all matrices omega such that eta mu nu identity plus omega mu rho identity plus omega nu sigma equals eta rho sigma to order epsilon. And that's the same as the set of all 4x4 matrices omega such that omega mu nu is minus omega nu mu. So again, antisymmetric matrices. But beware, right? You know, these, see how I've raised this index here up to here to get omega with two contravariate indices. If I had expressed omega in terms of a contravariate and a covariant index, then this condition is different, right? There'll be a metric tensor. So the tangent space to the Lorentz group, the Lorentz transformations, is a set of 4x4 antisymmetric matrices with two covariant indices. And there's you know, we're free to choose a basis. And we'll do exactly that. We can express omega in terms of, well, how many 4x4 antisymmetric matrices are there? Well, if we look over here, we can kind of guess, right? You know, all the diagonals must be 0, and once you've specified the upper triangular entries, you've specified the lower triangular entries by antisymmetry, and so there are 1, 2, 3, 4, 5, 6 such matrices. So we know that we can express any one of these guys as a sum of a linear combination of some basis matrices JA. And I'm going to write out a very particular basis that we use quite often when talking about Lorentz transformations. Now, for reasons that aren't going to be really obvious at the moment, I'm going to change this index A, which gets summed from 1 to 6, to a double index. So we're going to change this A, which runs from 1 to 6, to instead identifying each of 1 to 6 with a pair of indices rho and sigma, which run from 0 to 3, but with this additional constraint that rho must be less than sigma. So there's a bijection between these two index sets. So the number 1 gets mapped to 0, 1. The number 2 gets mapped to 0, 2. And then I may as well write out the full bijection. So that's the full bijection between these index sets. And there's a reason why we do this. And that's because we can write down an explicit basis for this space that exploits this notation to make it simpler. That's why the strange notation, because we can express a basis in this very nice formula here. It's an exercise for you that indeed that is a basis. And in fact, the problem sheet for the coming week will involve some more computations with exactly this basis. All right, the next part of my summary of the theory of continuous Lie groups is to illustrate, rather than actually prove, how the Lie algebra structure, an algebra structure on this linear space, gives you a Lie group structure and vice versa. So I'll sketch how that's derived. So first I'll argue that understanding the linear space near the identity tells you about the whole Lie group, which is kind of astonishing, right? If you look at something infinitesimally close to the identity, you somehow learn about the global structure of the manifold that you're on. And the reason that is that multiplication is a continuous map, and so is taking inverse. So that strongly determines the shape of this manifold. So any element of the tangent space to the identity determines an element of the group. This is really cool, right? So you let X be an element of this tangent space, and then you build identity plus epsilon X, yes? And we know that that's an element of the group up to first order. That's how it's defined, right? And I'm going to write that as e to the epsilon x to first order. So this is meant to be an element of the group to order epsilon. Now, because multiplication is continuous, we can multiply these guys together. So we're going to define g of epsilon to be that thing where we've multiplied elements of the tangent space like that together n times. Oh, I don't want to make that epsilon, I want to make that s. So at some point, as n gets bigger and bigger and bigger, s over n becomes epsilon, becomes smaller and smaller and smaller. This multiplication map is continuous, and we get a honest member of the Lie group as a consequence. So this is, not surprisingly, denoted e to the sx. So every element of the tangent space to the identity determines, by this repeated product here, an element of the Lie group. And in terms of vectors and flows, this is very easy to understand. So here's a picture of a Lie group. It's the sphere. This is actually an excellent cartoon for O3. Here's the identity up here. Now, an element of the tangent space is a tangent vector to the sphere. So that's some two-dimensional vector, right? That's x there. And what this map is doing is saying, go along the sphere, along a geodesic, a distance s, in the direction x. So you go along the great circle, a distance s, around the sphere. That's what the exponentiation map here is saying. Go in the direction of s. Keep walking in that direction. And then you'll end up at a point in the manifold. That point is called the exponential of sx. So to every tangent vector and a value of this parameter s, we get an element of the group by this exponentiation map. For sufficiently nice Lie groups that are connected, you can go backwards, right? You take every element of the group by taking a logarithm, gives you an element of the tangent space of the identity. And that element is what you need to exponentiate to get back to where you came from. right, now let's find an algebra structure on a tangent space, because we know we have a group structure on the manifold, right? We said there's a multiplication map that's continuous. What consequences does that have for the tangent space? And the answer is very interesting. Since M is a group, then we know that the group commutator of G and H is also an element of the group. It's a thing called the group commutator. It looks different from the commutator you're used to in linear algebra. We're going to see that in a moment. But this is an object that's defined in group theory. G is in the group, H is in the group, G inverse is in the group by definition, H inverse is in the group, and all their products are in the group. So definitely that's an element of the group. And it turns out, thus, the group commutator is a map from M cross M to M. And we're going to study what does this map do on the Lie algebra on this tangent space. Well, of course, it turns the tangent space into a Lie algebra. Notice the somewhat confusing looking equation if you're a physicist here. That's because for groups, GH is the commutator of G and H is defined like that. Now the important thing about any operation you do on a group is that it pushes forward to an operation that you do just on the tangent space. I'm going to use exactly the same notation. And the way you get this new map is you just expand everything to order epsilon and keep terms, or epsilon squared, depending on what's the first non-trivial thing. Okay, so I'll show you how we actually derive this map on the tangent space. All right, well, what you do is you substitute in place of G, I plus epsilon x, in place of H, I plus epsilon y into that expression. Now the inverse of I plus epsilon x is E minus epsilon x, is identity minus epsilon x. So we know that that's an element of our group manifold from star. So this is star here. So we're going to expand everything out and see what we get. So the first two orders are 0 in this group commutator. Yeah, I guess I'll do it differently. So the first term is indeed, there's an order 1 term, right? You multiply out the identity 4 times, you get the identity. That's definitely there. Plus you get nothing in order epsilon. You can check, I think, pretty quickly just by looking at it that the order epsilon term is 0. You get an x and a y, and then you get a minus x and a minus y. They cancel out. So the first term that you get is at order epsilon squared. And you know what? I'm going to change this, actually. I'm going to put a delta here to indicate that these are independent parameters. So the first non-trivial term to order epsilon, first order in epsilon and first order in delta is this object here. A delta, there must be, oh yeah, yes, there must be a delta here. Thank you. There you go. Now it is better. So we learned that this element is also an element of the tangent space to the identity of the manifold. This so I'm using the same notation for the group commutator and for this Lie algebra commutator. So as long as you remember where these things live, then you know what definition to use. So big X's and big Y's live in the tangent space. Little g's and little h's live in the group. So you know which commutator definition to use. Now, for our examples. Well, U1 is trivial, right? The commutator is just identically 0. So O3 is interesting. In fact, it's the most interesting example we've had so far in physics. And we derive that expression for the commutators. I did not actually check that before I prepared this course. I'll just do a quick computation here. Just to check that this works. There might be a minus sign that's wrong here. 0, 0, 0, 0, 0, minus 1. There's a minus sign, right? In terms of the basis I gave in the example. And the third example is the Lorentz group. So this bilinear operation bracket on the Lorentz group, you can work it out. And it's a very good exercise. In fact, it's such a good exercise that it is an exercise for you. and it's a bit lengthy. So there's 4 terms in this expression. But in essence, it's completely straightforward. So this is the formula you get when you multiply these basis vectors here according to this Lie bracket. And I gave you a formula for, indeed, these 4x4 matrices that are the basis vectors for the Lie algebra. I'm going to show you one example. And then the exercise, the problem sheet this week will be to do this in general. I've deliberately left this formula here. So we can write out some of these elements. J01, we have a nice formula up there for it. Let's write it out. It's a 4x4 matrix, and I got that for it. And what's the other one I did? J12. That's J12. And you can multiply these two matrices together and work out their group, the Lie algebra commutator. And you should end up with, if everything goes correctly, minus J12, which equals following 4x4 matrix. One, zero, zero. And the problem sheet will have you do this for all of them. Now, because the Lorentz group is such a special, important group in physics, and it's therefore, and people have studied it for a long time in various applications, people have developed lots of specialized notation just to deal with this particular Lie group. And I'm just going to introduce you to a little bit of this notation. Right now, we give special names to these generators for the special role that they play in Lorentz transformations. So the first special element is J01. That's called K1 in the literature, quite often called K1. J02 is called K2, and J03 is called K3. Yep. Should there be a J13? The question was, should this be J13? Well, that's a good question. That is J13. Thank you, you're right. Very well spotted. That's what happens when you count your indices from 0 or 1. Off by 1 errors happen all the time. So especially if you use MATLAB and you do relativistic computations, then you end up with these mistakes all the time. Because I check these in MATLAB, so that's why they might be off by 1 errors. All right, so we give these guys special names. These are called the boost generators. If you exponentiate these guys, you'll end up with a 4x4 matrix, which is a pure boost. It's pretty cool. It's definitely worth doing in MATLAB. Just exponentiate those guys and just see the pure boost come out. Very nice. Of course, there's 3 more generators that we have to worry about in the Lorentz group, and they are the pure rotations. Just to be consistent with what I wrote before, I'll put a factor of 1/2 in there. And the other guys, as I said, are the generators of rotation. And then there are the generators of rotations. J12 is called J1. J01, sorry about that. J01 is J1. J12 is J2, and J13, sorry, 2, 3, no, 1, 3 is J3. Oh, hang on, yeah, I messed it up, haven't I? Sorry. One, 2, 1, 3. Now it's all 2, 3. And those are the generators of pure rotations. But look, we knew that already, right? See this 3x3 matrix in here? That's exactly the negative of one of these generators over here. So the rotations live inside as a 3x3 submatrix, the Lorentz transformations. The rotations are a subgroup of Lorentz transformations. And that's it. We've actually described all the generators of the Lorentz group by taking linear combinations of these 6 elements here and exponentiating. You can get any Lorentz transformation. Just a quick word on representations before we get to getting our final representations. Suppose you can find a representation of the Lie algebra. what does a representation of a Lie algebra mean? It means a linear map from the tangent space to the manifold to some space of matrices. Because so far these are abstract objects. We don't have, they only become concrete when you can write down a matrix that does the same thing as them. So a representation is a linear map from the tangent space to the identity of the manifold to the linear operators. Let's call them bounded linear operators on some Hilbert space H. Well, not any linear map is good. Of course, you want that the Lie bracket property is preserved. Then the amazing thing is that this exponentiates to a representation of the full group. I mean, everything is continuous. And we get a representation for the full group just by exponentiating the representations. So this is the fantastic thing about Lie algebras and Lie groups. So you can either study the representations of Lie groups, try and find matrices that obey the group law, or you can opt instead to focus on the Lie algebra of the group, which is a linear space a linear space, and try and find matrices that do the same thing under this bracket here. And that's often an easier job. It's not so hard to do that. And you can then, through this connection here, just directly get representations for the group. And so that's why people will talk about representing a Lie group, but then always work with the Lie algebra. Because they know that although they haven't actually presented explicitly the matrix elements of the representation of the group element, all you have to do is exponentiate it, and then you'll have the representation. So that's that's really one of the most powerful parts of this story, is that you can get the representations this way. And that's how we're going to do our representations for the Klein-Gordon field. We're not going to represent a general Lorentz transformation. Instead, I'm going to write down operators, pi x, which represent the generators of Lorentz transformations. The actual Lorentz transformations are exponentials of these generators. And that's what we did before with the translation. So with the translation subgroup, we wrote down the generators of translations, which are momentum operators. All right, so almost there. We'll soon know how to implement a general Lorentz transformation on the Hilbert space of states of this Klein-Gordon field. And we do this via the Noether theorem and what we might call the inverse Noether theorem. So Noether theorem So for each symmetry of the field, X gets mapped to e to the epsilon some generator of the So for each of these Lorentz transformations here, these infinitesimal Lorentz transformations, there's a corresponding conserved current. One of per each of these J sigma mu's. J rho sigmas. That means there's 6 conserved currents. There's 6 generators. And we're going to denote them with a calligraphic J. Each one of these currents is a 4 vector. That's why there's the J mu. And how many other? There's 6, depending on this index rho sigma up there. And we worked out that they are equal to this combination of the stress energy or energy momentum tensor. So we've already worked that out in a previous lecture. Forgot what lecture it was, like lecture, was it 2 or 3? Guess it was 2, right? And then this gives us conserved charges. Q rho sigma equals the spatial integral of that expression there. And then we argued, yeah, question? Oh, thank you. Shouldn't the mu be 0 is the question, because conserved charges are only the time-like component. Indeed, that's correct. Yeah. Sorry. It is indeed 0. Now, Noether's theorem is kind of like, shuffling around. It's just a very fancy telescoping sum in disguise. But the inverse Noether theorem, I think, is really what is surprising and powerful, and extremely rarely discussed in textbooks. The inverse Noether theorem says that these conserved charges are the generators of exactly the symmetry transformations they come from. They generate canonical transformations on phase space giving a representation of our symmetries on phase space. So this is really, I find that much more profound, actually, than the Noether theorem. So this is I find this completely amazing because, well, everything's trivial on some level, I suppose. But here, you use the symmetry transformation to construct a conserved current, and then you somehow throw out a lot of information by integrating over all space and focusing on the time-like component. And just these functions on phase space somehow still know about the structure of the symmetry transformations that led to them. And they do so by generating these canonical transformations according to the Poisson bracket that obey exactly this Lorentz group Lie algebra. This is pretty fantastic. And it's an expression like that that gives us our hint. This is the clue for writing down representations of the Lie algebra in our quantum space. Because remember, the standard quantization story is that Poisson brackets go to commutators. And so we hope by putting on hats, we'll end up with a representation of our Lie algebra in our field. Because we know what this thing is in terms of field operators. We know how to put hats on these things. So we sincerely hope that we're going to write down some Hermitian operators that obey the Lie algebra of the Lorentz group. And then hence, we'll have a representation of the Lorentz group on state space. So this works. This works for free theories. This idea of using Noether's theorem and the conserved charges. But things fall apart when you go to interacting theories, and all kinds of horribilities can occur. And that's why relativistic interacting quantum field theories are especially challenging, because this trick of putting on hats no longer works. And you have to work very hard to argue that your theory is in fact Lorentz invariant after putting in interactions, even if the interactions look invariant. So let's put the hats on. We're going to put the hats on in the simplest possible way we can imagine, and it will turn out to work. Okay, that's our proposal. Now we're not done yet. We have to check, does it work, right? This is the crucial final calculation. Does it work? Does it obey the Lie algebra of the Lorentz group? Well, in this particular case, yes, it does. And so we get lucky. It will continue to obey the Lie algebra of the Lorentz group for any free theory that's got some constraints on the spin. As soon as we add interactions, this whole story falls apart. But we can celebrate that at least today we'll know one representation of the Lie algebra of the Lorentz group in the context of one quantum field. And let's just do it. Let's write it out in terms of our specialized notation kj. Okay, these are supposedly the generators of boosts. Let's hope they generate boosts then. So something should pop out at you as you look at that expression, and that is that it seems to be time dependent. We have another expression for t naught j, that's the momentum operator, right? So this is minus t, the momentum, total field momentum operator, plus the integral d3x of the Hamilton density quantized. That's what this expression equals. But we must be a bit careful because all of this depends on time. So this part depends on time, and this part depends on time. If this x wasn't here, this would be time independent. But because this x is here, this expression depends on time. But the whole thing is still time independent. Because it's the generator of boosts. Which means that this term has to the time dependence here has to cancel the time dependence here. And indeed that happens. So let's take the derivative of the right-hand side there. What do we get? We get minus pj hat plus, and here's the interesting bit, how does an operator evolve in time in quantum mechanics? Well, according to Schrödinger equation. So that's just the commutator with h. So you might think, doesn't h commute with h? No, h commutes with h integrated over space. This is the Hamilton density. The Hamiltonian does not commute with the Hamilton density. So that's an important observation to make here, which is why this is not trivial. But the Hamiltonian does indeed commute with the momentum operator. So what I can do is write this expression like this. Oops, there's a minus I here. And we've just learned that the boost generator commutes with the Hamilton operator to give a translation, which is as it should be. So if you do an infinitesimal shift in time and then a boost, then that's the same as doing a infinitesimal shift. I think I've got a minus sign error here. Plus, minus. What did I do wrong? Ah, yeah, it's a plus, right? So this is a minus. And similarly, we can work out the rotation generators. These are actually a bit easier because they're time independent, manifestly time independent. So we've managed to express in terms of our field operators, because the field operators are in there, they're in here. We've managed to express every possible generator of the Lorentz group as some operator in terms of these field operators like this. So So to finally do a Lorentz transformation on our Hilbert space, we take these field operators, we put some parameters in front of them, and we exponentiate them. And that's how you do a Lorentz transformation on your state space. What I haven't just about haven't checked, but I haven't even asserted yet that these generators obey the right Lie algebra. So okay, it's an exercise. I'm going to write out the answer, but it is an exercise for you to check all the appropriate commutation relations work out. So at least for the Klein-Gordon field, we're going to have so you go through, you put in this exact representation here into the commutators, you work out the commutators with lots of canonical commutation relations, and you should end up with this list of commutators here. So it's a somewhat tedious exercise, but pretty quickly you'll be able to do it fast, because you'll notice many cancellations that occur when you encounter commutators in here. And so this is the full Lie algebra of the Poincare group, which I haven't actually written out, but which I'll leave as an exercise for you to derive. So we've managed to show, modulo some exercises, that the Klein-Gordon field gives us a representation of the full Poincare group. So we can now do, if you want to do a Poincare transformation on a state of Klein-Gordon particles, there is a unitary transformation which does it, found by exponentiating these operators here. Yep? Question? Oh, I did use the exact opposite sign. Sorry, that should be. I think that's now fixed, isn't it? H, K, KJ, H. Now IP, and there's a minus there. Yeah, good. Minus signs don't matter because that just corresponds to changing a basis vector by a sign. I's don't matter because that corresponds to changing your basis vector by a factor of I. So it's more what bracket the results of the brackets is. Okay, so with that, I thank you very much.